Hello friends, in our last video we have completed the Fermat theorem and examples on Fermat theorem. In the today's video we will see what is Euler's theorem, statement, proof of the Euler's theorem and some examples on Euler's theorem. The statement for Euler's theorem is if a and n are any two positive integers such that a and n are relatively prime to each other, that is the GCD of a and n equal to 1, then prove that a raised to phi of n is congruent to 1 mod n, where phi of n is number of integers less than n and relatively prime to n. The statement, I will repeat the statement. If a and n are any two positive integers such that a and n are relatively prime to each other, then prove that a raised to phi of n is congruent to 1 mod n, where phi of n is number of integers less than n and relatively prime to n. So we'll prove this result here. So we'll consider the numbers which are less than n and relatively prime to n. Those numbers will consider as a1, a2, a3, so on up to a phi of n. These are phi of n in number because we have studied the Euler phi function, that is number of integers less than n and relatively prime to n is denoted by phi of n. So therefore a1, a2, a3, so on up to a phi of n, these be phi of n integers less than n and relatively prime to n. Now consider numbers a1, a2, a3, so on up to a phi of n, which when divided by n leaves the different reminders lying between 1 and phi of n. Yes, here I will take some example. I will take n equal to, I will take any one number, that is 7 I will write. Then the numbers which are less than n, so that is 7 and relatively prime to 7 are all the numbers from 1 to 6. So here a1 equal to 1, a2 equal to 2, a3 equal to 3, a4 equal to 5, and a4 equal to 4, a5 equal to 5, and a6 equal to 6. These are the numbers. Next, here we'll consider again a as any one number that should be relatively prime to 7, that is n. A and n must be relatively prime here. So we'll take a is equal to, I will take as a number as a 2. Clearly 2 and 7 are relatively prime to each other, so I have taken a is equal to 2. Now we have to multiply these numbers. First number here we have to take as a1. Means this a you have to multiply for a1. A1 is 7. 1 here. A1 is 1. So you have to multiply that 2 to a1. That is a1 equal to, we are getting as a 2. Next, a2 is equal to 4. a3 equal to 6. a4 equal to 8. a5 equal to 10. And a6 equal to 12 we are getting. Now what you have to do, we have to divide these numbers by n. N is 7. So dividing 2 by 7, remainder is 2. Dividing, so in the next line I will write only the reminders here. That dividing these numbers, so here I will write reminders. First number we are getting 2. Next divide 4 by 7, remainder is 4. Divide 6 by 7, remainder is 6. Next 8 by 7 you have to divide, remainder is 1. Next 10 you have to divide by 7, you are getting remainder 3. Next 12 you have to divide by 7, remainder is 5. Now observe these reminders. Whatever reminders you have got, those reminders you have to observe here: 2, 4, 6, 1, 3, 5. That is 1, 2, 3, 4, 5 and 6. So that is what we have written here. There's the reminders when a1, a2, a3, so on up to a5 of n divided by n leaves the different reminders. See, all the reminders are different itself, and those lies between 1 to 6. That is 1 and phi of n. 6 is here phi of n. So lies between 1 and phi of n here. So otherwise, suppose if any two of these reminders are equal, for example you have considered their way got all are different. In general, suppose if any two reminders are equal, that is what AR and AAS leaves the same reminder R1 when divided by n, then that is what if A R1 and A, that is AAR and AAS, these are the two numbers from these we have to consider. If you divide those numbers by same number, that is divided by n, then if those leaves the same remainder, then we are getting what we get here. So that is AR is equal to R1, that is remainder R1 when divided by n, and AAS divided by n, remainder R1 itself. Then by using these two, we can write AAR minus AAS is congruent to 0 mod n. Then by using congruence definition, we can say here n divides AAR minus AAS, in that A is taken as a common. So we got n divides A minus A into AR minus AS. Now as n divides these product, we must have n divides A or n divides AR minus AS. But we know that n and A are relatively prime to each other, therefore n does not divide A. Therefore we must have n divides AR minus AS, which is also not possible, because what we have here, AR minus AS is less than phi of n less than n. As this AR minus AS is less than n, it should not be divided by n here. Therefore AA1, AA2, so on up to A phi of n leaves the different reminders when divided by n. Already I have taken the example also. Therefore those reminders will consider as a R1, R2, R3, so on. That is what when A1 is divided by n, remainder R1, and so on. A phi of n divided by n, remainder R phi of n. Now multiplying all the congruences, we are getting that left side congruences we have to multiply. We are getting AA1, AA2, so on up to A phi of n is equal to R1, R2, so on up to R phi of n mod n. Again, in this A is taken phi of n times A is the product that we have taken outside, that is A1, A2, so on up to A phi of n, and right side it is R1, R2, so on up to R phi of n mod n. But A1, A2, so on up to A phi of n, and R1, R2 up to R phi of n are in some other order, means those are equal but in some different order. So we can try to replace that. This product we can replace by this product, or both side we can cancel it. We're getting A raised to phi of n is congruent to 1 mod n. That is our required. It is why it is A raised to phi of n, means this A multiplied phi of n times. Therefore A raised to phi of n is congruent to this, both get cancels, remaining it is 1 mod n. It is Euler's theorem. Now some examples we'll consider on this Euler's theorem. That is, first example, prove that phi of m square is equal to m into phi of m for all m belongs to m. So here let m is equal to, we'll consider any one number. We know that any natural number n can be expressed in the product of primes in a unique way. So by using that, we can take an m equal to p raised to a, q raised to b, r raised to c, and so on, where p, q, r, and so on are distinct primes. A, B, C are any positive integers. Now phi of m, we know how to calculate phi of Euler's phi function. We have calculated already by using the formula of Euler's phi function phi of n. We can write phi of m is equal to m into 1 minus 1 upon p into 1 minus 1 upon q into 1 minus 1 upon r, and so on. It is not terminated, because here it is not only a product of three terms, it is extended. So that we have taken as equation 1. Also m square is equal to, m is equal to p raised to a, q raised to b, r raised to c, and so on. So that m square is equal to p raised to a whole square, that is p raised to 2a, q raised to 2b, r raised to 2c, and so on. So therefore phi of m square is equal to m square, here m square into 1 minus 1 upon p, 1 minus 1 upon q by using the formula. So 1 m I can write outside, remaining m into 1 minus 1 upon p, 1 minus 1 upon q, and so on. So now replacing by equation 1, we are getting phi of m square is equal to m into phi of m. So that is the required. Phi of m square is equal to m into phi of m here. Now the second example, if p is a prime number, then prove that 1 raised to p minus 1 plus 2 raised to p minus 1 plus 3 raised to p minus 1 plus and so on, p minus 1 raised to p minus 1 is congruent to minus 1 mod p. If p is a prime number, then this is congruent to minus 1 mod p. You have to prove. We know that since p is a prime number, phi of p is equal to p minus 1. This formula also we have. Whenever p is a prime number, then phi of p is equal to p minus 1. That is 1, 2, 3, so on up to p minus 1 are relatively prime to p. Then by Fermat's theorem, we have 1 raised to p minus 1 is congruent to 1 mod p, 2 raised to p minus 1 is congruent to 1 mod p, 3 raised to p minus 1 is congruent to 1 mod p, and so on. P minus 1 raised to p minus 1 is congruent to 1 mod p, because 1, 2, 3, so on up to p minus 1, these are all relatively prime to p. Then by using Fermat's theorem, we have written these congruences. Now adding all these above congruences, we are getting left side 1 raised to p minus 1 plus 2 raised to p minus 1 plus 3 raised to p minus 1 plus and so on plus p minus 1 raised to p minus 1 is congruent to right side 1 plus 1 plus 1 p minus 1 times you have added is p mod p. Then sum of these is p minus 1. Therefore, what we have, this is left side 1 raised to p minus 1 plus 2 raised to p minus 1 plus and so on p minus 1 raised to p minus 1 is congruent to p minus 1 mod p. But we have p minus 1 is congruent to minus 1 mod p. Therefore, 1 raised to p minus 1 plus 2 raised to p minus 1 plus and so on p minus 1 raised to p minus 1 is congruent to minus 1 mod p. Or similarly, you can prove that 1 raised to p, 2 raised to p, 3 raised to p, so on up to p minus 1 raised to p is congruent to 0 mod p. Sum of all these is congruent to 0 mod p also we can prove it. The next example you consider, if p and q are different prime numbers, then prove that p raised to q minus 1 plus q raised to p minus 1 is congruent to 1 mod p into q. If p and q are two different prime numbers, then p raised to q minus 1 plus q raised to p minus 1 is congruent to 1 mod pq. You may consider any two numbers as a p and q as a different prime numbers, and we can consider. See, for example, simple numbers I will consider. Numbers I will take as a p equal to 2 and q equal to 3. Both are the prime numbers here. We'll consider p equal to 2 and q equal to 3. Now see, p raised to q minus 1 means p is 2, 2 raised to q minus q is 3. 2 raised to 2, 2 square is 4 plus. Next is q raised to p minus 1, q is 3, 3 raised to 2 minus 1 is 1, that is 3. So what we have here? 7. It is congruent to 7 is congruent to C. When you will divide this 7 by p into q, p you have taken is 2 and q is you have taken is 3, p into q is 6. 7 divided by 6, your remainder is 1. So therefore this 7 is congruent to 1 mod pq, that is 6. So therefore always, it is not only for this one, any two numbers, different prime numbers you consider, we are getting this result. So that will prove theoretical also. Since p and q are prime numbers, that we have different prime numbers, then p and q must be relatively prime to each other. Therefore, by Fermat's theorem, what we have, p raised to q minus 1 is congruent to 1 mod q and q raised to p minus 1 is congruent to 1 mod p. That is by using Fermat's theorem. Now, p raised to q minus 1 is congruent to 1 mod q and q raised to p minus 1 is congruent to 0 mod q. This is because we have, that is whenever q raised to p minus 1 is divided by q, we are getting remainder is 0. So therefore, now adding these two, p raised to q minus 1 plus q raised to p minus 1 is congruent to 1 mod q. That is equation 1. Similarly, q raised to p minus 1 is congruent to 1 mod p. Here we are by using Fermat's theorem. Q raised to p minus 1 is congruent to 1 mod p and p raised to q minus 1 is 0 mod p. So again, adding these two, we are getting q raised to p minus 1 plus q raised to p minus 1 plus p raised to q minus 1 is congruent to 1 mod p. Now from equation 1 and 2, what we have? P raised to q minus 1 plus q raised to p minus 1 is congruent to 1 mod pq. Because these p and q, these two are different prime numbers, we can keep these as it is. You have to multiply the numbers here, that is these prime numbers you have to multiply. So we are having p raised to q minus 1 plus q raised to p minus 1 is congruent to 1 mod pq. This is what about Euler's theorem and some examples related to Euler's theorem, Fermat's theorem and Euler's phi function. Next concept is Wilson's theorem, that we'll see in the next class.